Hi, my name is Tiago, and I'll present this paper called A Bayesian Framework for Information-Theoretic Probing. This was joint work with Fry and Cotterell. So, as a quick introduction, in another paper, we previously analyzed probing from an information-theoretic perspective. And what we argued in the paper is that probing may be viewed as approximating the mutual information, this mutual information between a probed property and the contextual representations. So, counterintuitively, the contextual representations contain exactly the same information about any task as the original sentence. This is what we showed in the paper. But this seemed rather unintuitive though, since pre-trained models do help in practice. So they seem to make more information available to our models when we're applying them in real scenarios. So a quick background in information theory is that it defines many metrics relevant when analyzing data and their probability distributions. But these metrics are traditionally defined according to a true probability distribution, P of X, which may not be known, like you may not know what probability distribution this P of X is, but it dictates the behavior of the random variables X and Y. So among these metrics are the entropy and the mutual information. And something that is usually overlooked is that in his seminal work, Shannon was thinking about the analyzing the limits of communication. So in a sense, the mutual information can be described as a theoretical limits or upper bound. How much information can be extracted from one random variable about another if you had full knowledge about these random variables and their probability distributions. But the question that is left is how should information flow in scenarios where these true distributions are not known? And in this work here, we'll analyze information from the perspective of Bayesian agents. So agents which have some uncertainty about how to model the world, how to model the probability distribution P of X. So we'll operationalize these agents as a probability distribution, P theta of X given theta, and a prior P of theta. So this is a typical Bayesian model. And as usual, this agent's posterior over theta will be given by this equation here, like P of theta given D of n, where this D of n here is we're conditioning on the previously observed data. So this is a set of instances X that the agent has observed before. And analogously, we can model the predictive posterior as this integral integrating over theta, integrating out theta to get the P of X given the n. And we'll call this the belief of the agent. So what it believes that the probability distribution of X should be, given that it's only seen D of n instances of this distribution before. So now we'll analyze information from that perspective. So this agent surprisal upon encountering an instance X will be given by this equation. So the surprisal won't be minus log of P of X itself, like with the true probability distribution, but the log of the belief of the agent itself. That's how surprising the agent is when it sees a new instance X. And we will define the Bayesian entropy as this second equation here, which is the expected value of the Bayesian surprisal taken over the true distribution. So you're taking the expectation with respect to the true distribution, but using taking the expectation of the Bayesian surprisal. So this is actually a cross entropy instead of an entropy. And we do this instead of taking the entropy of the belief itself, because we want to have the value, the average value of the surprisal, but grounded in the real world. So what the agent will encounter in real life. So that's why we have a cross entropy here. And then we can define a Bayesian mutual information similarly as the difference between two Bayesian entropies, the Bayesian mutual information. But there is an important distinction between the Bayesian and the Shannon's mutual information. Bayesian mutual information decomposes as two cross entropies, while Shannon's mutual information decomposes as two entropies. And this will be important. And another thing that we'll show here is that the Bayesian mutual information is a generalization of Shannon's mutual information. So in the paper, we show several theoretical properties of these models. We'll show some of them here that we think are important. So the first one is the data processing inequality that says that running a function through a random variable y, for example, f of y, can only reduce the amount of information it encodes. But the data processing inequality does not hold for Bayesian mutual information, which means that you can make more information available to a Bayesian agent by processing a random variable, so y becoming f of y. The second one is its relation to mutual information. So under a weak assumption, Shannon's mutual information upper bounds the Bayesian mutual information. This is interesting because, as we said, the mutual information is this theoretical limit, this upper bound, and then a Bayesian agent will only be able to extract a subset of the information that is encoded in the random variables and not all of it. And the other property here is that if the Bayesian agent's beliefs are well formed, meaning that the Bayesian agent's belief can model the true probability distribution, then in the limits of infinite data, the Bayesian mutual information will converge to the true mutual information. So the Bayesian mutual information is a subset of the total amount of information, but if you expose the agent to enough examples, it will slowly converge it. Another property is its relation to V information. So V information is similar to the true mutual information, but it defines like what is the amount of information available if you could only extract it with a specific variational function. So a variational family. So a specific set of functions. So for example, if you can only extract information using linear functions, how much information would be available? And we show in the paper that Bayesian agents beliefs, if the belief is not well formed, which means that the true distribution is not a possible belief, then the Bayesian mutual information will actually convert to the variational family, variational information instead of the true mutual information. Finally, the last property we want to talk about here is that usually you can decompose the cross entropy like this, right? Like the cross entropy of X equals the entropy of X plus a KL divergence between the true probability distribution and the belief of the agent. But what we show in the paper is that we can rewrite this equation, the KL term, as this Bayesian mutual information, the mutual information that the instance X gives you about the model parameters themselves. So about the distribution you're trying to model. So this is interesting because in a sense, no information is being lost. The cross entropy that your agent is experiencing decomposes as the information, the entropy about X. So the information the agent gets about X, plus the information that X is giving it, the agent about the distribution of X itself, so about theta. So this is a plot with a summary of the previous things and about like how Bayesian mutual information works. So these are Bayesian agent learning curves in green and orange. So the cross entropies of the Bayesian agents. This here is the Bayesian mutual information itself, which is the difference between two Bayesian entropies. This here shows that the Bayesian mutual information can be negative. And this happens when you have a Bayesian agent with a weak prior exposed to some evidence, and then it can overfit to the evidence, and then the conditional Bayesian entropy can be higher than the unconditional one. This term here represents the information the agent is extracting from the data set about its parameters itself, and which will be the difference between the Bayesian entropies and the true entropy of the data. So it's how much data the agent is extracting about its model parameters. And this is related to the surplus description length from a paper in iClear earlier this year. So we see here that although it doesn't increase monotonically, the Bayesian entropy kind of grows as you're exposed to more data, and then it slowly converges to the true mutual information in the limits of infinite data. So now let's go into probing. So we'll now apply Bayesian information to analyze contextualized representations, and we will analyze this Bayesian mutual information here from the contextual representations to a probed property conditioned on a specific amount of data D of n. So first, let's do some theoretical analysis of what we expect. We have no a priori knowledge of how representations should impact the prediction. So the prior Bayesian mutual information should be 0, which means that given 0 data, the conditional Bayesian entropy and the unconditional one should be the same. On the opposite extreme, if you have unlimited data, a well-formed belief will converge to the true distribution, which will yield the same results as of our previous paper. And an ill-formed belief will converge to the V information. So you have this nice relationship here where the Bayesian mutual information will be equal to the V information in the limits of infinite data, which might be close or the same as the mutual information itself if your model is well formed. So what Bayesian mutual information answers is this question: given a specific data set, how much information do the representations yield about this task? So it measures, it kind of measures ease of extraction, how much information can be extracted from the contextual representations by a naive agent with no a priori knowledge about the task itself, given only a limited amount of data to try to observe and learn the task. So going into our results, these are the plots for post-tagging. And we see that information is much harder to extract with random embeddings, which are the pink points, than, for example, with the fast text ones, which are the blue ones. But we see, especially in English, that given enough data, the random embeddings results slowly converge to the fast text ones. And given infinite data, in theory, they should exactly match. So random embeddings do encode the same mutual information as fast text ones about any task under small assumptions. What else we see here is that Albert makes more information more easily extractable than BERT or Roberto in English, and multilingual BERT is roughly equally informative as fast text under the finite data scenarios of the other 3 languages. But multilingual BERT does encode more information than fast text if you were considering the infinite data scenario, so the true mutual information. So now going to dependency parsing, by looking at these curves, we see that it seems to be an inherently harder task than post-tagging. So while post-tagging curves seem to be converging, this is not the case for dependency arc labeling. The agents are still learning, even given all the data in this data sets. Furthermore, for low data settings, the BERToids models hurt performance. So given their high dimensional representations together with a weak prior, the agents overfit, and then you have negative mutual informations. It is especially easy to see in the English example, where you see that for the low data examples, you have negative Bayesian mutual informations. So going back to your previous paper, in there we argued that contextual representations contain the same information about the task as the original sentence. And this is true. And what we claimed is that under this lens, probing was nonsensical. But here we show that given infinite data, a well-formed probe or a well-formed Bayesian agent will converge to the true mutual information, and the previous result will still hold. So what we conclude is that given infinite data, pre-training does not help, which makes sense, right? Like you're pre-training, and then you need less data for fine tuning. If you have infinite fine tuning data or infinite probing data, the pre-training does not help. So under this lens, probing only makes sense in finite data settings. So we should be conscious about like what finite data means in our analysis. So to conclude, we analyze information from the perspective of a Bayesian agent, and this leads to more intuitive results in finite data settings. Data can be informative, processing can help, and information can hurt. We then use Bayesian mutual information to probe representations. Our weight is more informative of the analyzed representations in English, and high-dimensional representations may hurt in low data scenarios. Thanks for watching this presentation, and I hope I'll see you at the poster session.